A single filament of scorching plasma can reshape entire galaxy clusters, and the first one on our list is a phenomenon most people never even imagine. Stay tuned until the final entry to see the most surprising stream. Imagine a beam of plasma traveling at nearly the speed of light, blasting out from the heart of a galaxy and extending for hundreds of thousands of light years. These relativistic jets are launched by supermassive black holes that feed on surrounding matter, converting gravitational energy into focused streams of superheated gas. As the infalling material spirals inward, magnetic fields twist and accelerate particles, creating narrow, luminous columns that can pierce the intergalactic medium. Observations across radio, X-ray, and optical wavelengths reveal that jets not only heat surrounding gas but also regulate star formation by blowing away cold material that would otherwise collapse into new stars. Researchers estimate that a single powerful jet can deposit energy comparable to billions of supernovae, reshaping the host galaxy's evolution and influencing the temperature of the surrounding cosmic web. This interplay between black holes and their environments underscores how even the darkest objects can drive some of the hottest, most far-reaching phenomena in the universe.
Consider the chaotic aftermath of a galaxy undergoing a furious bout of star formation, where countless massive stars explode as supernovae within a few million years. The combined energy from these explosions creates a collective outflow known as a superwind, a colossal gale of ionized, superheated gas that can escape the galaxy's gravitational grip. These winds travel at speeds of several hundred kilometers per second, carving cavities in the interstellar medium, and transporting metal-rich material into the surrounding halo. By doing so, they enrich the circumgalactic environment with heavy elements essential for future generations of stars and planets. Simulations suggest that superwinds can suppress further star formation by removing the cold gas reservoir, effectively acting as a self-regulating mechanism for the galaxy. Observations of nearby starburst galaxies, such as M82, showcase spectacular filamentary structures glowing in X-ray and H-alpha light, providing a vivid illustration of how stellar birth and death can jointly launch some of the universe's hottest, most influential gas streams.
Surprisingly, our own Milky Way harbors two enormous, balloon-shaped structures rising tens of thousands of light-years above and below the galactic plane, known as the Fermi Bubbles. Detected initially in gamma-ray observations, these bubbles are filled with superheated plasma reaching temperatures of several million degrees. Their sharp edges and uniform brightness suggest a rapid, energetic event in the galaxy's recent past, possibly linked to past activity of the central supermassive black hole or an intense starburst episode. As the bubbles expand, they push against the surrounding halo gas, creating shock fronts that heat and accelerate particles to relativistic speeds. The exact origin remains debated, but estimates place the energy injection at around 10 to the power of 55 ergs, comparable to millions of supernovae. These structures not only illuminate the dynamic nature of galactic nuclei but also demonstrate how episodic events can drive massive, hot outflows that shape the Milky Way's circumgalactic environment.
Hidden within the luminous cores of distant quasars are powerful outflows that eject superheated gas at velocities reaching tens of thousands of kilometers per second. Powered by accretion onto supermassive black holes, these outflows manifest as broad absorption lines in quasar spectra, indicating massive amounts of ionized material being flung outward. The gas, heated to millions of degrees, can travel far beyond the host galaxy, influencing the intergalactic medium, and distributing metals across cosmic distances. Researchers estimate that quasar-driven winds can carry mass outflow rates of hundreds of solar masses per year, rivaling the galaxy's star formation rate. By injecting energy and momentum, they may quench future star formation, thereby regulating galaxy growth. Although direct imaging remains challenging due to their great distances, indirect evidence from absorption features and theoretical models underscores the crucial role of quasar outflows as some of the most energetic, hot gas streams shaping the large-scale universe.
Few people realize that the iconic radio galaxy Cygnus A hosts colossal lobes filled with plasma heated to tens of millions of degrees, extending over 1 million light-years on either side of its central engine. These radio lobes are inflated by twin jets launched from a supermassive black hole, which deposit energy into the surrounding intergalactic medium, creating shock-heated cocoons. X-ray observations reveal that the lobe's interiors are dominated by ultra-hot, low-density gas that exerts pressure on the ambient environment, preventing cooling flows that would otherwise lead to rapid star formation. Estimates suggest that the total energy stored in the lobes exceeds 10 to the power of 60 ergs, making them among the most powerful known reservoirs of hot plasma. By continuously feeding this energy back into their surroundings, the lobes serve as a prime example of how black hole activity can generate and sustain massive, superheated gas streams that sculpt the large-scale structure of the cosmos.
Recent simulations and observations have uncovered faint, magnetized filaments threading the cosmic web, where diffuse gas is heated to temperatures of a few million degrees by shocks and turbulence. These filaments act as highways for hot plasma, channeling material between galaxy clusters and feeding them over billions of years. While their densities are low, the sheer scale, spanning tens of megaparsecs, means they contain a substantial fraction of the universe's baryonic matter. The heating arises from large-scale structure formation, where collapsing matter generates shock fronts that compress and warm the gas. Detecting these streams is challenging, but indirect evidence comes from subtle X-ray emissions and the Sunyaev-Zeldovich effect. Understanding these magnetized, superheated filaments is essential for completing the inventory of ordinary matter and revealing how energy is redistributed across the vast tapestry of the universe.
Even the most massive structures in the universe can generate spectacular hot gas streams when they collide. In merging galaxy clusters, the intercluster medium, already at temperatures of tens of millions of degrees, forms shock fronts that further heat the plasma to even higher temperatures. These shocks propagate through the cluster at thousands of kilometers per second, compressing magnetic fields and accelerating particles to relativistic speeds, which then emit radio relics observable as elongated arcs. The resulting superheated regions can reach temperatures exceeding 100 million K, dramatically altering the thermodynamic state of the cluster. Observations of the bullet cluster and the sausage cluster illustrate how these violent encounters redistribute energy, strip away cool cores, and influence the future evolution of the constituent galaxies. Such events highlight the dynamic, ever-changing nature of the cosmic landscape, driven in part by these enormous, hot gas streams.
Beyond the bright disks of galaxies lie vertical channels known as galactic chimneys, where superheated gas from stellar feedback bursts through the surrounding interstellar medium into the halo. Formed by clustered supernova explosions and intense stellar winds, these chimneys can funnel plasma at temperatures of a few million degrees, creating fountains that rise thousands of light years before cooling and raining back onto the galactic plane. The process transports energy, momentum, and metals far from the star-forming regions, influencing the chemical evolution of the galaxy's outskirts. Measurements of emission lines in edge-on galaxies show that chimneys contribute significantly to the hot ionized medium, accounting for a sizable fraction of the galaxy's total X-ray luminosity. By venting excess heat, they help regulate the pressure balance within galaxies, illustrating how localized, superheated gas streams can have far-reaching effects on galactic ecosystems.
Massive O-type and Wolf-Rayet stars unleash continuous winds that accelerate to speeds of several thousand kilometers per second, heating the ejected material to temperatures of several million degrees. These hypervelocity winds carve out bubbles of hot plasma around the stars, known as stellar wind bubbles, which can merge with neighboring bubbles in star-forming regions to create vast, interconnected chambers of superheated gas. The collective effect of many such stars in a cluster can generate a large-scale outflow that escapes the galaxy's disk, contributing to the enrichment of the circumgalactic medium. Spectroscopic studies reveal that the wind-driven plasma emits strongly in X-ray wavelengths, providing a direct probe of the heating mechanisms at play. Though each individual wind is localized, together they represent a pervasive source of hot gas streams that shape the thermal and chemical landscape of galaxies over millions of years.
Finally, cosmologists predict that a substantial portion of the universe's ordinary matter resides in the warm hot intergalactic medium, a tenuous network of gas heated to 10-510-7 K by the gravitational collapse of large-scale structures. These streams thread between galaxies, flowing along the filaments of the cosmic web and delivering material to forming clusters. Though extremely diffuse, the sheer volume means the WIM contains up to half of the missing baryons. Detection relies on subtle absorption lines in the spectra of distant quasars and faint X-ray emission, making it one of the most elusive yet crucial components of cosmic matter. As the gas accretes onto clusters, it is shock-heated, joining the broader family of superheated streams that drive the evolution of the universe's architecture. Understanding the WIM is essential for completing our picture of how matter cycles through the cosmos, from the smallest galaxies to the grandest superclusters.
We've journeyed through 10 of the universe's most powerful, superheated gas streams, each a reminder that invisible forces can sculpt the grandest structures we see in the night sky. Understanding these streams helps us grasp how galaxies grow, how clusters merge, and why the cosmos looks the way it does today. If you enjoyed this deep dive, subscribe so you don't miss the next mind-blowing list we release each week. Let me know in the comments which stream you found most astonishing, and if you liked the video, give it a thumbs up. Thanks for watching, and keep looking up.